well as the other measurements made by LRO, were important factors in determining the impact target for LCROSS. Now, I want to move on to our neutron detector, LEND. The animation here shows a LEND mounted on the bottom of the spacecraft. LEND was supplied by Russia to NASA for LRO. It's a high-resolution neutron spectrometer. And the beauty of LEND is that by searching for regions where there's a shortage of low-energy neutrons, you can infer the presence of hydrogen in the first meter or so of the lunar surface. Now, the left-hand side gives the first map of the lunar South Pole made with a resolution of about 90 kilometers, comparable to previous missions. The blue indicates regions that have a shortage of low-energy neutrons, which is consistent with the presence of hydrogen there. Now, with time, LEND will be doing finer mapping as it acquires more data. The right-hand image is the LEND data to date with a 30-kilometer resolution, and ultimately, over the next few months, we'll make maps with a resolution of about 10 kilometers. Now, the surprising thing about the LEND observations are that, first of all, it confirms that there is hydrogen near the lunar South Polar region. What it also seems to indicate is that the hydrogen is not confined to permanently shadowed craters, that some of the craters, permanently shadowed craters, do indeed contain hydrogen. Others, on the other hand, do not appear to have hydrogen. And in addition, there appears to be concentrations of hydrogen that are not confined to the permanently shadowed regions. Now, as we go along and improve the quality of the LEND data by repeated observations, this early measurement will be verified and refined, and we'll be able, after the next few months, be able to tell you where the hydrogen, which is presumably associated with water, where it is located at the lunar South Pole. Now, the next instrument is also aimed at looking at hydrogen or water at the South Pole, and that's the LAMP ultraviolet spectrometer. This is very similar to a system that's now en route to Pluto and to a comet. A LAMP is a very sensitive UV instrument, so it was the last instrument to be turned on. It's only been operating for the last few weeks, and we only have a few passes over the South Pole. This map shows in color the ground track of the data that's been acquired so far. LAMP works by looking for the signature of water frost on the surface by ultraviolet absorption. You see the insets below, which show passes over Cabeus and also over Faustini, a permanently shadowed region, a permanently shadowed crater. And over Faustini, it shows a distinct darkening of the ultraviolet emission, which could be due to a surface texture effect, or it could be due to the presence of water frost there. We need to make more measurements to verify this, but indeed these data show that LAMP is extraordinarily sensitive and it's working very well. LAMP will also be used to measure the lunar atmosphere and is the prime instrument for supporting the LCROSS observations. LRO is going to pass over the LCROSS impact site a few minutes after the impact. LAMP will be used to search for the volatiles, the artificial atmosphere that's created when the ejecta comes out of the LCROSS impact site. Well, let me move on to LROC, the LRO camera. This shows in the animation our two narrow-angle camera apertures in the wide-angle camera system. As you've probably all seen images already from LROC. LROC was turned on in early July. We released very promptly images of the lunar surface from LROC and made a major effort to target the Apollo landing sites So those beautiful images could be released in time for the anniversary celebration. LROC is mapping the lunar surface, even now in the commissioning orbit. We show here a map of the lunar south polar region. The bright part of the crater you see there is the Shackleton crater, which is nearly at the lunar south pole. We now zoom in so that you see the fine resolution that's available. The resolution of each of these pixel elements here is about 1 meter, so that the smallest objects you can discern in this image as we slowly pan across the surface is about the size of an automobile or smaller. And then we're right now going across very close to the lunar south pole, which is right near the rim of Shackleton. This is the rim wall that's illuminated by sunlight. You can see the texture here. You can see boulders. You can see evidence of fresh craters. You can see smooth landing sites that would be appropriate for robotic or a human return to the moon. And it's data like this will be important not only for science but also for exploration. Now this single image, which is only about 5 kilometers or 3 miles across and about 50 kilometers long, contains roughly 1 gigabyte of data. It was just in the past hour put online at Arizona State University and is accessible through the NASA website. We've so far released several dozen images from LROC, each of which is about a ½ gigabyte in size in order to make them available promptly. So now we have one more instrument on LRO, and that's our laser altimeter system. And Dave Smith, our Lola PI, is going to tell you more about it.
Thank you, Rich. Yes, Lola is a laser altimeter. It measures the distance between the spacecraft and the surface. And we have a video of what that behaves like. It sends 5 pulses down to the surface. They are reflected back. We measure the time it takes for the signal to go to the surface and come back again. And from that, we make the real measurement of the instrument itself. It does this 28 times a second for each of those 5 pulses, so 140 measurements per second are being made of the elevation of the surface below the spacecraft. Now, because the surface of the moon is not nice and flat, the reflection of these 5 pulses provides information actually about what we will call the roughness of the surface and the slopes, and that's actually very important for us. And so this is used in mapping eventually the total surface of the moon, and as Rich said earlier, this will be used to kind of be the framework for all the other observations because it will geolocate everything we have. Now, we do have a map of the southern hemisphere, at least a portion of it. This is a 600-mile square area. The South Pole is right in the middle. This is just the Lola data. We will look at a piece of that in the middle, which is the Shackleton crater in a moment. The range of elevations is from about -7 kilometers to +7 kilometers. So it's about 4 or 5 miles high and 4 or 5 miles low is the full range that we've got in this region. And it's very typical of the moon. It's not the highest or the lowest, but it's very typical. And you can see the craters very clearly there. You can see the central peaks. You can see some rings in some of the craters. And the red area is, in fact, the very large, high elevation area, which actually provides shadowing for parts of the moon. And in a moment, I will show you the next chart, which actually looks at the central region of this and shows what the shadows are like just a little while ago. But first, let's see what the instrument has acquired during the first 30 days of commissioning. So we have approximately twice as much data as in fact shown here. And here you can see the colored lines mapping out the southern part of the moon, where we obtain data, and you can see it coming around and slowly filling in the gaps until you move towards the South Pole itself, where it's not quite full yet, but it is full enough that we can actually really map the terrain at the level of let's say a meter or two or thereabouts, and each spot on the surface, by the way, is only 5 meters in size. So we're looking at some very high resolution